In the last video, we discussed about XYZ coordinate system and how it become inefficient when it comes in the curvilinear path. XYZ coordinate system is better defining the position of a particle, but when it comes to describe the motion itself, the particle XYZ became inefficient, and that is where NTZ and R-theta-z coordinate come in the picture. But in this video, we are going to describe how NTZ coordinate system fix the problem of dealing the behavior of motion of a moving particle in a curvilinear path. First of all, the main statement that I want to point out is that it's not that XYZ can't be used, but NTZ make the same problem simple solving. Think like you use different tools to solve a different problem. You can use an oxen cart vehicle to travel 10 miles, but you will use your car or a different vehicle to travel faster and efficiently. And that is how coordinate system work, and it's all about choosing the right coordinate system based on this specific problem. For example, if you want to find out the position of a particle, you use XYZ coordinate, but if you want to find out the behavior of the motion, you will use NTZ coordinate system. But as always, we are going to see from system level. Before going towards NTZ coordinate system, worth knowing the history about NTZ coordinate system. So there were two people, their name comes when in NTZ coordinate system. These were Frederick, Frenet and Joseph Alfred Serret, both mathematicians, worked independently, made this system, also called Frenet-Serret system. In Frederick researched and published on 1847 and Joseph Alfred Serret 1851. So the first question that the system level asked, why NTZ coordinates? What was the question that was asked? So the result was NTZ coordinate system. And for this thing, the answer is quite simple. When you use XYZ coordinate system to describe the behavior of a moving particle in a curvilinear path, you have to first do the math. For example, you know the path x equal to r cos omega t and y equal to r sine omega t. And if you want to find the velocity, so what will you do? You will take the derivative first, because the derivative of distance is velocity. So it will be minus r omega sine omega t and y equal to r omega cos omega t, I mean phi. And then if you want to find out the acceleration of this particle in a curvilinear path, so you have to again do the derivative, because the differentiation of velocity is acceleration, and you will get negative r omega square cos omega t, and here you will get r square sine omega t. You see, we are doing the math first and then we will deal with the physics. But in NTZ coordinate system, you can just directly deal with the physics of motion. XYZ become messier when you do the math and when you do the differentiation and everything all. But NTZ coordinate will make your life a lot easier. But before describing the formula of NTZ coordinate system, let's us understand what does this term mean. What is n? What is t? What is z? Or they also call tangential, normal and binormal coordinate system. But let's just describe what does this term mean. Example, if I draw the x and y axis and if I put a curvilinear path, and let's say this particle is moving along the curvilinear path and here, so what is tangential? Tangential always act along the motion of the object. It is straight to the path and always act towards the velocity. And if the velocity is forward, it is forward. But if you reverse the velocity, the tangential flips direction. So tangential is direction of motion plus speed change. And remember the point, it always acts towards the velocity and is defined by a tangential is equals the differentiation of velocity with respect to time. So what about normal? Think this as the radius of curvature. So the normal always act towards the radius of curvature. If the straight line is the tree, the normal will act along the radius of curvature and is always perpendicular to the tangential. And the formula of acceleration in the normal plane is v square over r, where v is the velocity and r is the radius of curvature. But here is the catch. How do you find r? Back in our calculus days, if you remember, we learned about the curvature of finding the length of curvature, and we denoted it with kappa. When we were finding the oscillating circle, we used a formula kappa is equal to f double derivative and then 1 plus f single derivative whole square and 3 by 2. But when we were about to find out the radius, we have to divide 1 by kappa and it will just flip. So our radius will be 1 plus fx whole square power 3 by 2 f double x, and this is in absolute. So this is how you find out the radius. But unlike XYZ coordinate system, where the center was treated as a reference and from the center anything we could measure, but in NTG coordinate system, the particle is itself the center. For example, this is a particle A is moving in a curvilinear path, and this is tangential, this is normal, and this particle is behaved as the reference or the center itself. Now let's take NTG coordinate system one step deeper and understand what are its input, internal interactions, output, constraint, and uncertainty. So if I'll write its input, what do you think the input is? Velocity and path. Remember the curvilinear. And what is its internal interactions? Curvature of path. So this is the object. And what are its output? If we calculate all of these, why? Because we want to describe the motion, its acceleration. So the output will be acceleration. For example, you describe acceleration as acceleration in the normal direction plus acceleration in the tangential direction, and then you find the magnitude of acceleration using the sum of the square of both terms under square root. And now talking about the real world examples, because this is where concept really clicks in. And the first of all, what comes in your mind first if I say an object moving in a curvilinear path? Our one, solar system. And this was the question as well that scientists develop in NTG coordinate. They want to describe the motion of the particle of our solar system of planets that is rotating around the sun in a curvilinear path. So you say this is our sun and this is earth. Well, it should be in the center. So this is sun, this is the radius of curvature, this is towards the velocity in the tangential direction, and this is in the normal direction. So they want to describe the acceleration in the normal direction and in the tangential direction. So it also used to learn our own solar system, a radial hydrogen turbine. If I will show you an image from my own project, I need to copy this first, delete it from here and paste it over here. So as you can see, this is the back plate of the compressor side, and when you see these all blades will be rotating in the clockwise direction, and as you can see it's a curvilinear path. So if you put some hydrogen, the hydrogen will itself behave as a particle, and the particle we have to calculate the acceleration in the tangential and the acceleration in the normal along the radius of curvature. So suppose this is radius of curvature and we have the hydrogen particle on this side, and this is acceleration at tangential and this one is acceleration towards the normal. So this is the second example, the turning turbine blade. The third example can be roller coaster. If you have seen a roller coaster, suppose this is an object which we assume that as a particle, and in the roller coaster the path is curvilinear as you can see. So it also helps to calculate the physics or the stability of the particle. For example, we can calculate the acceleration towards the normal and the acceleration towards the velocity direction. And here comes the next part, the G part, which is also called binormal. So binormal is basically the cross product of acceleration toward normal and acceleration toward tangent, or you can say normal and tangent. So the binormal is always perpendicular towards the normal and the tangent. One statement to remember, XYZ coordinate system explain the position, while NTG coordinate system explain the motion of the particle, but there is still something slightly off here when it comes to the geometry part, and that is where R-theta-z coordinate system come in the picture. We will see in the next video what problem we still have and how does R-theta-z coordinate solves that. Till then, what problem NTZ and XYZ doesn't solve that R-theta-z solve it. Write in the comment box below and we'll meet in the next video. Till then, thanks for watching.